We have all seen it happen. You click a shiny Submit button, and suddenly the entire interface completely locks up. This happens because JavaScript is single-threaded. It can only process one instruction at a time. This sequence of instructions is processed in a specific region of memory known as the call stack. If you execute a massive synchronous operation, like a loop counting to 1 billion, it occupies the stack completely. No other code can run. That is the physical cause of the UI freeze. To keep applications responsive, the browser must offload heavy tasks, like fetching network data or waiting on timers, to the background. Preventing UI lockup is the exact reason asynchronous JavaScript exists. To handle that offloaded work, we rely on callbacks. To understand how callbacks execute, we must map the engine, the call stack, web APIs, and macro task queue. When you invoke an asynchronous function like setTimeout, it immediately moves out into the web API environment. The web API handles the actual waiting in the background. Meanwhile, the call stack is free to execute the rest of your application's code. Once that background timer finishes, the web API places the function into the macro task queue. This is where the event loop intervenes. It acts as a gatekeeper with one strict rule. It only moves items from the queue to the stack when the stack is completely empty. Callbacks are the runtime's native mechanism for taking work that was offloaded and returning it to the main thread safely, without causing an execution collision. This mechanical timing creates an edge case that frequently traps developers in technical interviews, placing a setTimeout inside a for loop using the var keyword. The loop runs synchronously. It rapidly iterates, scheduling 3 timeout callbacks into the web API. Because the loop is synchronous, it finishes entirely before the stack empties. The variable mutates to its final value of 3. Only then does the event loop move the callbacks to the stack. By the time they execute, they all reference that exact same mutated variable. Anyone can memorize syntax. Comprehending this timing discrepancy separates basic coders from engineers who understand runtime state. As applications scale, callback architecture introduces a well-known visual symptom, Callback Hell, or the Pyramid of Doom. When you nest multiple asynchronous network requests, the code logic drifts further and further to the right across the screen. This deep indentation makes the logic difficult to read and maintain. You can refactor that logic by extracting those nested blocks into separate named functions. Visually, the code is now completely flat, yet the fragility remains. You are still manually chaining state between functions that are inherently coupled. The fundamental structural weakness of the callback pattern persists, threatening your application's stability even after the visual pyramid is completely flattened. This structural weakness stems from a concept called inversion of control. When you pass a callback function to a third-party API, you hand over the execution authority of your own code. You are treating that external API as an opaque system. You supply your function and trust the API to handle it correctly. But that external system might call your function too early, too late, multiple times, or never at all. By trusting a black box, you inject an external, untraceable defect straight into your application's runtime. This is the core of the problem. Developers no longer dictate when or even if their own logic runs. The ultimate consequence of this inversion is seen when attempting to use a standard synchronous try-catch block to wrap an asynchronous callback. The try block executes, schedules the callback via the web API, and immediately pops off the call stack. The safety net is gone. Later, the event loop pushes the callback onto an empty stack. If an error occurs now, the callback is completely isolated. The error drops down the stack, searching for a catch block. It finds nothing, and the program crashes. Asynchronous programming breaks traditional exception handling. To survive the demands of the modern web, the runtime required a completely new, resilient architectural primitive. That primitive is the promise. It was engineered specifically to solve the inversion of control crisis. Instead of handing a callback into a black box API, the API immediately returns a placeholder object representing future data. Holding that receipt allows you to attach your own handlers. You retain complete control over the execution flow. Promises also introduce the microtask queue. This is a higher priority lane built exclusively for promise callbacks, ensuring they execute as soon as the stack is clear. This structural shift restores linear execution guarantees and unifies error propagation through the .catch method, protecting the single-threaded runtime. We have traced the journey from a vulnerable, blocking call stack to the uncontrollable risks of the macro task queue. Promises represent a strategic shift in authority, allowing developers to govern execution within an inherently unpredictable environment. Visualizing the runtime as a predictable mechanical state machine allows for the construction of highly resilient, industrial-grade software. Mastering these under-the-hood mechanics is the defining characteristic that elevates a junior developer into an advanced JavaScript architect.